Hi, and welcome to today's presentation from Avantor, which is looking at troubleshooting methods in gas chromatography. My name's Tony Edge, and I'm the site director for the Hycron facility where we manufacture a range of different chromatography consumable products. I'm delighted today to be joined by our partners MacMod, who are an authorised channel partner. MacMod have been a trusted partner for over 20 years with expertise in HPLC and UHPLC and more now in gas chromatography as well. So I'm really delighted that we're able to do this webinar in conjunction with them. In terms of what we're going to talk about today, I want to focus on really 3 or 4 areas. The first is to try to get a good understanding of the different gas chromatography components. This will be important when we're looking at the troubleshooting aspects in particular. One of the major items of concern is the column installation, and making sure that we get that correct will ensure that we have less troubleshooting to do with our methods. And so I'll put a little bit of focus on terms of the column installation, and then we'll move into the bulk of the presentation, which is looking at various troubleshooting aspects, identifying what the issue is that we're seeing, and then looking at some probable causes that could be contributing to the artifact that we're seeing. And then finally, I'll wrap up with a conclusion section. So moving then to the GC itself. The GC comprises of a variety of different components, which we can see in the figure attached. And so we start on the bottom left with our gas cylinder. This could be hydrogen, could be helium. It then will go through a gas filter of some description to try and remove the bulk of any impurities that are within the gas supply. For chromatography, we need very high purity gases, and the cylinders that are commercially available may not necessarily be up to that specification. So it's important that we purify the gas through a gas filter. From there, we then move to the injector. And this is where we introduced our samples. And then from the injector, we then go on to the column. And typically this will be a wrapped coil for a gas chromatography column. This is placed in a column oven. And the reason for that is that we use temperature in order to elute our components of interest off the column. And then as they elute off, they go through some type of detector and then into a data capture device, in this case a PC. Murphy's law states that if anything can go wrong, it will go wrong, and all of these individual components can cause issues in terms of the process of performing gas chromatography. This, in conjunction with the raw sample as well, are all of the individual components that we need to consider quite carefully when we're looking at our troubleshooting. In order to introduce the sample, we would typically introduce it using a syringe with a needle, and it's important that we choose the right type of needle in order to make sure that, one, we don't damage the instrumentation, but also that we get the correct transfer of the sample from the sample vial into the column. The most commonly used form of needle will be the cone or tapered tip, which we can see at the bottom, and that's typically used for a variety of different types of injectors. If we're looking at a manual injector, then we may go for a bevel or a sharp tip one, and you can see on this diagram here why it's called that. If we're looking at headspace or large volume injections, then we may go for a side hole, and this is simply where the exit to the needle is at the side of the needle as opposed to the bottom of the needle. For injections which are either on column or where we're using some form of injection valve, not a septor, we might use a blunt end. And where we're looking at injecting directly into the column, so for a on column injector where we inject onto a megaball column, we may look at a needle design that is actually tapered to allow us to inject directly into the needle. The gauge number that is often quoted with the needle is a measure of the thickness, with high numbers relating to a thinner gauge, something to be aware of when you're injecting, as this will impact the stability of the needle going through any septa, etc. This is the design of a typical type of GC order sample or GC injector. What we can see is at the top we have a septa and a septa nut. Our sample will typically be introduced through the septa into the vaporization chamber, which is below it. This vaporization chamber is heated, and it's heated in order to ensure that we get volatilization of the sample, and therefore we can then perform our gas chromatography. If we look at the gas supplies, the first thing we see is the carrier gas inlet. Part of the gas will flow out through the septum purge outlet, and this is to remove any volatile components that may be coming off the septa. And again, making sure that we have a right flow rate selected here will ensure that we remove the bulk of the debris coming off the septa. When we then look further down, the vaporization chamber has a split vent outlet, and what this means is that we can effectively segregate the column into a component that goes onto the column and a component that goes off to waste. So we have the split vent outlet, and this ratio between the flow going onto the column and the flow going out the split is referred to as a split ratio, and is important for ensuring that we get good sample transfer and we also don't overload the column. In terms of the physical process, the needle pierces the septa and will be introduced into the vaporization chamber. At this point, the heating effect will start to volatilize the sample as it's introduced into that chamber, and it's important that we try to avoid any discrimination between compounds that have different boiling points. This can occur because the split valve will preferentially take off certain types of compounds related to their boiling point. We also need to at this point ensure that we don't have any adsorption occurring on any of the active surfaces. So here you'll see that we've got a gold seal at the bottom of the vaporization chamber. The liner we will choose to try and be as inert as possible, not only for adsorption, but potentially there is an issue with reaction kinetics occurring. So we're actually converting a molecule from one form to another with the surface acting as some form of catalyst. We also need to make sure that we contain the sample and it doesn't just go straight out the split vent. So careful control of the temperature within the vaporization chamber will ensure that. In terms of what can go wrong at this point is that the sample may not be introduced correctly. So I already talked about a certain amount of the gas flow going off via the septum purge. So if we introduce the sample too high, we could start to lose some sample in that area. Maybe that we've not heated the sample effectively. Could be that the septum seal doesn't seal, and consequently we get a flow of carrier gas going up out of the septa. The liner may not be appropriate. We may be having a more active liner than we should be using, and this could create a situation where we have a degree of adsorption, or indeed where we have some reaction kinetics occurring. At the bottom, we can see that the column, now if that's not fitted correctly, or the column hasn't been inserted high enough up into the vaporization chamber, then again that may cause some issues. It's important that the sample is evenly distributed between the waste and the column, and that we don't get any boiling point discrimination occurring. And there are ways in which we could do that, which we'll talk about later on in the presentation. In terms of other considerations when we're looking at choosing the injector type, it's very important to consider the type of sample that we are using, and also the type of application that we want to do. So are we looking at a trace level? Are we looking at a relatively dirty sample, or are we looking at a relatively clean sample? And here on the right we can see a variety of different types of samples that are commonly used in gas chromatography, ranging from urine to environmental analysis of some water products. If the initial sample is dirty, then we may need to perform some sample cleanup to remove some of those matrix components. So potentially some of the salts that we may find in urine, or some of the background matrix components that we may find in a water sample. And a good way of doing this is solid phase extraction. It's also necessary to be aware of other forms of types of analysis. So residual solvent analysis, is that what we're interested in? Are we looking at a solid analysis? And again, if we're looking at both of these, the injector selection becomes quite critical. It's also important to determine the volatility of the sample as well. If all of these are considered, then we should avoid problems with peak shape and sensitivity issues that can happen. If we don't consider these effectively, then we will end up with some issues in terms of peak shape and sensitivity. In terms of the different types of injection modes that are commonly used in GC, the most common is probably split-splitless. And this is where we look to split the flow coming in from the carrier gas. And so part of it will go off to waste, part of it will go onto the column. We can run this in a split-less mode. So that means that all of the sample is transferred across onto the column, as opposed to in a split mode where we only get a very small component transferred onto the column. This has impact in terms of the detection limit for both of those examples. So because with the split mode we are looking at splitting the sample, typically the detection limits are higher than we would anticipate with the split-less mode where everything is going onto the column. In terms of the suitability of these techniques, then the splitless injector is not really suitable for cold injections, and some degree of consideration has to be considered for the thermal degradation of the sample as it moves on to into that volatilization chamber. Another approach that is commonly used is cool-on-column. This is where you inject the sample directly onto the column. Therefore, there is a complete transfer of the sample onto the column, which then means that we get very good sensitivity, typically ranging down to 0.25 ppm, parts per million. The disadvantage with this approach, though, is that in order to inject onto a column, we need a wider bore column. So typically a 530 micron ID column in order to do this. It doesn't use a split line because all of the sample goes onto the column. And in terms of the way that the sample is heated, this is similar to the next one on the list, which is the PTV, or programmable temperature vaporization. The PTV injector is a more modern version, if you like, of the splitless injection. It has a much lower volume within the vaporization chamber, and it has a much higher degree of control in terms of the heating. In fact, we can actually get a heating ramp applied to the volatilization chamber due to the compactness of it. In terms of the sample concentration, again, it reflects very much what we would see with the splitless interface. There are advantages with this technique. The ability to control the inlet temperature and therefore the sample volatilization is incredibly important for removing any degree of discrimination within the sample. It also can be used with initially quite low Uden temperatures, which again may be quite beneficial. There are also other types of interfaces that allow for a volatile component, a volatile gas, to be introduced into the GC directly. Typically with this we'd be looking at a purge and trap or even a headspace. And again, when we're looking at the benefits of these, we can see that we can do a direct injection where we get very good sensitivity. We can have a look at the a split or a splitless, as with the original ones that I mentioned previously. Once the sample is introduced into the vaporization chamber, it then has to vaporize. And so in order to do this effectively, we really need to understand some of the GC liners that are typically used. So if we're looking at a split liner, then a split liner would typically have would be a tube of deactivated glass of some description that would allow for movement of the increased gas flow, because we're removing some of the gas. We don't want to cause restrictions. It is feasible to add glass wool, and we'll go through why that is important later in the presentation. If now we're looking at a liner that can do both split and splitless, then we may have a look at a tapered or a double tapered liner, and this helps us in terms of the sample introduction because it reduces discrimination of the sample, as I referred to earlier, and the tapered component helps to focus and direct the sample onto the column. For a splitless liner, we will probably have a tapered bottom. A couple of reasons for this I've already mentioned, but on top of that, it would also mean that we would have a less active surface. So we saw on that initial diagram of the GC that we had a gold plated surface or a gold surface which the liner came into contact, but ideally we want a very highly deactivated surface, and having a tapered inlet to the column makes a lot of sense here. I mentioned about the quartz wool. The quartz wool helps with the inertness of the liner, and what it does is that it enhances the vaporization process. This it does in a variety of mechanisms. The first is that it increases the active surface area over which the vaporization can occur, and also it enables a degree of mixing of the sample to ensure that we've got a degree of homogeneity during that vaporization process. In terms of the positioning of the glass wool, or the quartz wool should I say, then there are two positions. We could either have the wool towards the bottom, and in this position it traps non-volatiles and it helps to as an increase in the area for the sample to vaporize. If we have the wool nearer the top of the liner, then in this scenario, then the wool can be used to wipe clean the syringe and therefore reduce the contamination occurring from one injection to another. And it also helps in terms of the mixing within the chamber as well. I talked about a split injection, and it's important to be aware of the impact that changing the split ratio can have in terms of the performance of the chromatography. So here we've got a couple of examples where we're looking at a low split ratio and also a high split ratio. So on the top diagram we can see what happens with a low split ratio where we have a ratio of 1 to 5. In this scenario, the first eluting peaks have poor peak shape and there's a lot of peak broadening. If we look at the bottom one, where we've got a much higher split ratio, in this case 1 to 50, we can see that for peaks 1 and 2, we've improved the peak shape substantially. However, it is also important that helium is expensive, and as you increase the split ratio, we will be losing more of that expensive helium. And so, as well as the cost, there is also the sensitivity issue as well. Increasing the split ratio will increase the amount of sample going to waste as well. The other type of injector that I mentioned earlier on is cool on column. In terms of cool on column, there are a variety of things to look out for with this one. So in this scenario, the needle is being inserted directly into the column. So it is feasible that the needle could end up being bent, and this is often associated with the wrong size needle, and we talked about the type of needles that should be used with the mega ball columns. It's also feasible that a degree of burrs could be introduced into the sample at this point as well. It's feasible that the needle can get plugged due to septum coring. It's also possible that we see a loss of peak shape, and this could be due to issues with the column, and checking to make sure that there is no contamination of the column, either through a visual inspection or just monitoring the background, will give a good indication of whether or not there's issues here. The cool-on column is injecting all of the sample directly onto the column. As we inject in a liquid state, it is important to remember that there will be a substantial increase in that volume as the sample volatilizes. And so therefore the sample injections tend to be very low, typically of the order of 0.2 microliters or less. And so being aware of that and keeping to those smaller volumes will ensure that we don't effectively overload the column. It's also important that the inlet temperature is below the boiling point of the solvent being used as well, so we get complete transfer and effective transfer onto the column. In order to protect the column, we can use a retention gap, and this can also be used in order to focus some of the samples. We now move on to the column, and looking at the column, we can first focus on the ID and looking at what column ID we should be using and what are the advantages and disadvantages. So a typical ID column would be a 320 micron ID. The advantage of this is that it has a higher load capacity and also a lower back pressure associated with it. However, because of the larger internal diameter, we require higher levels of gas. It will also provide a lower resolution because of the Golay equation, and potentially it could also give us longer analysis times. This technique is, with the larger ID columns, typically will be used with splitless methods, gas analysis or headspace analysis. If we're looking at smaller columns, less than 320 microns, so 250 micron or 100 micron columns, then these columns will give us higher resolution. We use less gas, which is great, and we also start to see that these can be applicable for techniques such as fast GC. However, the disadvantages are that the reduced surface area of the tubing means that we've got less loading capacity, and also the reduced ID means that we've got an increased pressure. It's very important if we're using a split injector on these type of columns to make sure that we don't overload the column, and I've already given some examples of what overloading may look like. The next consideration is looking at the film thickness, and so in this scenario we are looking at different levels of coating onto the surface. So at the bottom we can see three examples of coating. What we have are the outside the polyimide coating that gives the flexibility to the silica, which is the fused silica on the middle bit, and then on the inside we've got the stationary phase coating, which drives the separation. The typical film thickness for the stationary phase ranges from 0.1 to 10 micron. And what we typically find is that the thinner the film thickness, the less time the analyte spends in the stationary phase, which gives us shorter analysis time, but perhaps less separation ability. So thicker films increase the time that the compound spends on the stationary phase, which gives us a longer analysis time, which may help, particularly where we're looking at permanent gas analysis, where we need to increase the retention time. As well as the film thickness and the internal diameter, we also need to consider the length of the column. Shorter columns will absolutely decrease the analysis time, and they may be suitable where there is not a requirement for high resolution. If we combine the short column with small IDs, such as in fast GC, we can maintain or even increase resolution. Longer columns obviously will give us better resolution, and where we see an increased length, when the ID can't be reduced, we'll start to see better resolution in that scenario as well. So if we're looking in terms of the typical types of use, if the column is less than 15 meters, then we're looking at short run times, fast GC, etc. A column of about 30 meters is a typical general use GC. If we're looking for very long retention times for specific applications, then we may be looking at columns that are 60 to 100 meters. In terms of increasing the resolution, increasing the column length will help. However, it is important to note that it is a last resort, and it's much better to look at the column selectivity than just increasing the column length. Typically, doubling the length of a column would increase the resolution by approximately 40%, but double the analysis time. It should be noted that the column should not be cut in half as well. If the column is cut in half, then the performance of the two halves that are produced cannot be guaranteed in accordance with the initial QC testing from the manufacturing. So we can summarize this up in this nice little table, and this talks about the film thickness, the length, and also the column ID, and the types of analysis that we can preferentially run on these different types of columns. It also goes through some of the advantages and disadvantages of those as well. We mentioned the film thickness of the stationary phase. So what stationary phases are available? We can look at the full range of gas chromatography stationary phases, ranging from high polarity, or should I say low polarity, to high polarity. So in this scenario here, we can see that the high 1 has a very low polarity. We then move to the high 5 at 5% bisphenol. And then as we move and increase the column polarity, we start to move to the wax and the polyethylene glycol, the PEG columns, which are used for free fatty acid analysis. So a range of different stationary phases that give us different selectivities for different types of compounds with different levels of polarity associated with them. In terms of what columns to use, so the most widely used is the 5% phenol, as I've mentioned previously, and this comes in a variety of different formats, ranging from columns that are compatible with mass spectrometry to ones that have very low bleed and are therefore compatible with higher temperature analysis. Similar also for the 100% polysiloxane, the high 1 column, which is a very non-polar apolar phase, and that has a variety of different formats. If we move to the more polar phases, they are typically based on polyethylene glycol, PEG, and again there are a variety of different phases that are available here that would suit different applications, ranging from coupling to mass spectrometry to high temperature analysis. Column installation is an important component of the process of making a GC work effectively, and it's important that we install the columns correctly. First thing to do is make sure that the system is cool and turned off. And so for those of you who've ever installed a GC column onto a hot injector, that's probably the first and last time you do it. It hurts a lot and it's not to be recommended. Make sure that the gases are clean going into the column, and so that ensures not just making sure that the gas cylinder has a reasonable amount of gas in it, but also that the gas filters are in good nick as well. This will avoid contaminating that expensive column on installation. With the injector, make sure that the injector is clean before attaching a new column, so that way we don't get any debris coming from the injector fouling the new column. And also look at the detector as well, so that when we eventually connect the column to the detector, no debris from the detector due to carbon, etc., falls into the column. When cutting the column, it is important that we do a clean cut, and there's a couple of examples of a clean cut and then a not so clean cut. That unclean cut can create issues with leaks, and that will mean that we see a loss of sample and the loss of peak shape as well. It's important that we don't cut through the column, but instead that what we do is that we score and then snap the column. Cutting the column directly will create a very jagged edge due to the way that the polyamide and the glass will interact when cut. Once we've got the column, we then need to make sure that we install it into the system correctly. It's important to choose the right type of ferrule, and we'll come on to that later. Ideally, we'd want to use a new ferrule on every installation rather than reusing an old ferrule, mainly because it may not seal that properly, or that if we're using a graphite ferrule, we may see some debris coming through. In terms of the alignment of the column, make sure that you read carefully the manufacturer's comments on this one from the gas chromatograph, so how that fits in. It's important to get the right setup in terms of the distance. Once the column is connected to the inlet, then turn the gases on and look to sweep any debris from the column out, and this may involve residual bonded phase that's not quite bonded effectively. It's also important to make sure that you perform a leak test at this point to ensure that there are no leaks coming from the inlet. Once this has been done, then connect the detector and then the column is ready for the next stage. I mentioned the ferrules. There are three common types of ferrules. There's graphite ferrules. These are reusable, so which means, and they're very malleable, so which makes it ideal if you're on a bit of a budget. However, they are porous to oxygen, and so really not ideal for MS detectors. They do have a tendency to flake though, and little bits of carbon can come off, which is why they're not recommended in changing or reusing a graphite ferrule when installing a new column. Another type of ferrule is the Vespel ferrule, which is a mixture of graphite and Vespel. This is ideal for mass spec detectors as it's non-porous to oxygen. However, they can shrink a little bit on heating, so it's always worthwhile that after the first couple of heat cycles on the injector that you go back in and retighten up that nut just to make sure that the seal on the Vespel ferrule is correct. There is also a Siltite, which is the metal equivalent to the Vespel ferrules, which are designed to be installed with finger tight applications. In terms of detectors, there are a range of different detectors that are available. A list are here of a variety of different 3-letter and 2-letter acronym ranging from FID, flame ionization detector, to PID, photoionization detector. It is important with all of these different detectors to make sure that they're operated under the correct operating conditions. If they're not, there will be a loss of sensitivity and or indeed a loss of resolution of the various peaks that you're looking at. With many aspects of troubleshooting, prevention absolutely is the best approach, and so performing routine preventative maintenance on the system really does help. So in terms of the things that you might want to change on a regular basis, replacing the liner, and this could be gauged on having a preset performance level for a particular analysis, if you like a system suitability test. If the system falls below that, then we would look to change the liner. The other one is the septum, and for this we would look to change that on a very regular basis, potentially even daily. It's also important to keep the injector and detector clean and well maintained. A lot of the issues that, as we'll discuss later on, can come from these components. It's also important to make sure that there are no leaks in the system as well. And then, as a general rule of thumb, having a preventative maintenance schedule at least once a year for the whole instrumentation makes a lot of sense. In terms of then troubleshooting, so we found that we have an issue and now we need to rectify it. It's always good to have an approach to troubleshooting. Always be systematic in the approach. record all data. Try not to assume too many things and go through, as I say, a systematic manner in order to elucidate what's happening. Ideally, start with the least time-consuming activities. And so if changing the sector is one of the key activities as opposed to reinstallation of column, that's much quicker. So look at that first and foremost, as opposed to perhaps something that takes a little bit longer. Always have in mind a plan B, and that plan B may be an engineer, but specify a time limit on this so that actually you're not wasting valuable analytical time trying to fix a problem that may be outside of your knowledge ability. And this is a quote that I got from one of my mentors some years ago, and I thought it quite a nice quote. And basically what he said was that I can save myself a 5-minute conversation by doing 6 months work in the lab, which clearly doesn't make sense, because why would we want to do 6 months work in the lab? But oftentimes as an individual, we won't be the first person to see a particular issue. So do talk to your colleagues to try and work out what actually is happening. As well as having an approach, it's also useful to have a toolkit, and the toolkit should contain a flow meter, a range of new syringes, and we've discussed what type of syringes we can use, a non-retained detectable compound, and there's some examples given in the slide there, methane or propane, a range of septa, ferrules, inlet liners, and other general consumables so that we can look to replace those. An electronic leak detector. We've already talked about a reference sample, but perhaps another type of reference sample that this time contains something that is less volatile. Having a reference column, a column that you know works, is also very useful. And then a range of tools and spanners that can be used on the instrumentation in order to change columns, etc. So let's go through the different areas. We're going to focus initially on baseline related problems, then look to peak related problems, and then look at some of the results related problems. Just to kind of give us hope that actually there is joy in this troubleshooting process. Here is a rather nice chromatogram of a separation of organophosphate pesticides on a high 1701 phase. We can see that we've got good peak shape, good sensitivity, good selectivity. So this is the ideal scenario that we'd like to see. Looking at the first one, it is feasible that we get a degree of baseline drifting occurring, and this can be caused by accumulation of impurities on the column. It could also be caused by accumulation of stationary phase, which can also result in extra or ghost peaks appearing or distorted peaks occurring. The carrier gas cylinder pressure may be too loud to control the gas flow correctly, which can be causing some issues. And drifting carrier gas or combustion gas flows can also be causing the problem of a drifting baseline, particularly when we're looking at the detector side of the instrumentation. In terms of the cure, the remedy, obviously check the purity of the carrier gas. Make sure that you're not running low on the gas cylinder and that the filters are all in specification and that are relatively new. If needed, replace the gas filters. If it's believed that it's the column, then look to remove the end section of the column in order to remove the possibility of impurities coming from that particular part of the column. If the gas cylinder is very low, then look to replace the gas cylinder. Perhaps increase the gas cylinder pressure just to make sure that the gas is going correctly. And that will be the gas cylinder pressure for both the carrier gas and also the detector gases as well. Make sure that the gas controllers are all working and that there are no blocked valves there. And if need be, look to replace the column with a new or a lower bleeding version. And with that, we should hopefully have no drift. As well as a variable baseline response, what is commonly seen in gas chromatography is a rising baseline, a typical sort of S-shaped curve. This can get enhanced and consequently can impact the analysis. So in this scenario, the possible causes could be a poorly conditioned column or one that's been exposed to an excessive amount of oxygen, and this can result then in a degree of phase decomposition that causes, as the temperature rises, the baseline detector response to increase. If we're looking at using the mass spectrometry, we can use that as a diagnostic tool in order to try and identify if it is the stationary phase or something else that is causing the problem. Typical masses to look for are 207, 281 and 149, which are common masses associated with the polysiloxane stationary phases that I've mentioned previously, or indeed any phthalates that may be present. It's also worthwhile making sure that there are no impurities in the gas line. Baseline falling can also be an issue. So with this one, it tends to be something associated either with the carrier gas and a loss of flow in the carrier gas, and this might be there's a leak. Could also be associated with a column that is baking out and we're starting to remove the excess of stationary phase, or it could be associated with an unequilibrated detector. Common examples here would be something like an electron capture detector, which are notorious for long equilibration times. In terms of a remedy, perform a leak test, check the tightness of the connections on the carrier gas line, and also allow enough time for the column detector in order to stabilize. If the baseline is falling away slowly after a high initial value, then the possible causes here are that the purge value has been left closed during acquisition. And so if we're looking at a splitless, we should open up the purge valve after a certain preset time. Maybe that there's an inadequate purge flow. Also, it could be associated with a solvent peak that's got a very long tail, and possibly pre-filters are dirty. This can be particularly the case when using a mass spec detector. In terms of the cures for this, altering the GC program, in particular the GC inlet part of the program, will be very beneficial. We can look at altering the purge flow rate, that again can help, and looking at, for the solvent peak, looking to increase the solvent delay so that we no longer see the solvent peak coming through, and look to shorten the purge time as well. And then for the pre-filter, obviously cleaning the pre-filter will be very beneficial here. Another aspect is a noisy baseline. Some possible causes here are contamination occurring in the injector or the column. Maybe that there's a defective detector. It might be that in the scenario where we're looking at an FID, an NPD, or an FPD detector, that the column has been inserted too far into those detectors, and so therefore the flame that is burning is not stable, and that causes noise. It might be that the detector temperature is higher than the column maximum temperature, and again that could be causing issues. Or it could be associated with loose column fittings. All of these are very easily remedied. And the way we'd remedy them is first is looking to clean the injector by replacing the septor and liners. We could look at baking out the column, and we'll talk about how to do that later. Potentially look to cut the first 10 centimeters of the column off. If that doesn't work, instead of keep cutting 10 centimeters off and eventually end up with no column, look to replace the column. With the detector, obviously make sure that we've inserted the detector correctly and that it's the correct distance within the detector as specified in the manufacturer's manual. For the temperature, again, look at the method conditions and make sure that the detector temperature and the column temperature match. And with the fittings, again, just go around and make sure that you've retightened the fittings, in particular, as we've mentioned previously, with the Vespel fittings. An S-lined baseline is something that we have seen previously, but there are other possible causes that can happen here. Excessive column bleed can be an issue. particularly where we're looking at a higher column temperature programming. Also, oxygen contamination can cause decomposition of the stationary phase that can cause this elevated baseline rise as we increase the temperature. Ways of eliminating this are to reduce the column upper temperature, so therefore it's the observed stationary phase bleed is not so observable. We could look to bake the column out, and the way we'd bake the column out is typically by either running at the maximum temperature of the column for about half an hour to an hour to remove any residual stationary phase, or if we're not running near the higher end of the operating conditions of the stationary phase, look at operating 10 or 20 degrees above the maximum operating oven temperature, again for the same sort of duration. Installing oxygen filters can also help, and making sure that there are no leaks on the system as well. Spiking, typically this is caused through electrical disturbances, and this is often associated with an FID, and it's often associated with a wrong column installation on the FID. That or the FID is running at too low a temperature, or that the jet going into where the flame is produced is slightly dirty. In terms of how we address that, we could look to make sure that we insert the column into the correct positions, and typically this will be 2 to 3 millimeters below the tip of the jet, and with most manufacturers pushing the column up until you get a degree of resistance and then pulling back a couple of millimeters will suffice in this area. It's also feasible that cleaning the jet and parts of the detector can also help as well. And then finally look to increase the FID temperature to at least 150 degrees C. The next section is going to be looking at peak related problems. So the first of which is overloading. And overloading occurs because we've injected too much stuff onto the column. And so this can be remedied very simply by injecting less, using a split at the injector, or looking to change the loadability of the column by using a mega bore or wider bore column. In terms of peak shapes, peak tailing is also problematic, and having a good indication of which peaks are tailing can be very useful in determining the root cause here. So if only some of the peaks are tailing, then it's probably a secondary chemical interactions that's occurring, and this may exist where we're looking at quite polar analytes that can interact with some of those siloxane surfaces in a different fashion. It may be that the inlet temperature is too low, could be that column degradation is causing a degree of activity, or the column is contaminated at the inlet that is causing a different type of stationary phase that causes these secondary interactions, or indeed it could be something associated with the liner. In terms of the remedies, increasing the inlet temperature can help. Looking to inject a test mixture and evaluate the performance of the column can also help determine whether or not we've got the right column. Is it column too old? We need to replace. Is the column just the wrong sort of column? We need to replace. And then looking at more drastic measures, potentially removing the first meter of the column in order to identify if it is actually coming from the column, or if we're running with certain detectors, look to increase the temperature of the transfer line. As well as chemical interactions, peak tailing can also be caused because of the solvent peak. And often, as we've seen previously, this can be occurring when we're running in a splitless injection mode and when high gas flow rates are used. The cause is a disruption in the transfer to the column, incorrect column position in the inlet, or the oven temperature is initially too high, or the septum purge flow is too low and the splitless line vent flow is too low. The remedy to all of these is to either reinstall the column, just check to make sure if you've got a vestibule fitting that you've retightened those up after a couple of operations, Look to reduce the initial oven temperature, and also look to make sure that on the method program that the septum, purge and vent flows are set correctly and that you haven't missed a decimal point, etc. Peak splitting is another common artifact that is often found in split mode, and here we can see an example of that. It might occur in splitless mode when using high gas flows, and again the cause is the disruption of the sample to the column. It can be remedied by increasing the injection speed or by looking at addressing the issues with poor column installation. Other possible causes could be poor injection technique. This should not happen with an order sampler, but if you're doing manual injections, it's something to be aware of. A poorly installed column in the injector can also cause this impact. Column temperature fluctuations, so particularly if the column is not just resting on the cage but is on the metal liner on the inside of the column oven, that can cause hot spots that can cause this. It may be that actually there's a coalition of two or more components that's actually causing what looks like peak splitting. It's just actually it's two peaks. In terms of the other factors, it may well be that mixed sample solvent for splitless. So having two different solvents can give differences in the retention times due to volatilization process for the splitless, or indeed on column injections. The wrong inlet choice as well can also result in the sample not volatilizing correctly, and consequently that causing issues with peak splitting. Other factors that can occur are peak fronting, and so here we can see a normal peak versus a fronted peak. If we see peak fronting, then the possible remedies are a decrease in the column or detector and reducing the overloading aspects of that, so that we've overloaded the column, so just reduce the sample amount. Perhaps the column temperature is too low. Perhaps we're not got enough stationary phase, so again a column overloading issue, but looking at having a thicker column stationary phase will address that, or poor injection technique. Other remedies would be decrease the injection amount, look to increase the split ratio or decrease the analyte concentration, increasing the temperature using a thicker film, or repeat with a better injection technique. Ghost peaks are something that we mentioned earlier, and we mentioned some of the possible causes earlier as well, such as contaminated carrier gas. It could also be contamination from laboratory glassware that has transferred into the sample. It could also be that we've got decomposition of the injected sample. Also, activity on the liner could be causing some issues here as well. In terms of the remedy, if it's a contaminated carrier gas, look to replace the cylinder and or the filter. Make sure that if we are doing any sample preparation, that the glassware is clean and contamination free. And then with regard to the injection port, make sure that we've got the appropriate temperature, or look to use on column injection technique, and that would remove any contamination coming from the injector. And then in terms of the sample, look to make sure that you carry out adequate sample cleanup prior to the injection. If it's the liner, very simply replace the liner. If we have negative peaks, these can be caused by a variety of things, typically associated with the incorrect polarity of the detector, and this can be associated with a thermal conductivity detector, or TCD, or the micro TCD. They can also be associated with detector overload. That can occur with certain detectors. I've listed some here: ECD, NPD, FPD, etc. A dirty ECD detector can also give negative peaks after a large positive peak. If you see no peaks at all, then potentially you're not injecting the samples. That could be a defective syringe if it's not gas tight. Talked about the septor and the importance of making sure that you replace the septor on a regular basis. If a septa is blown, then you could have a massive leak occurring at the injector port. The carrier gas is going out through the septa, and therefore you would lose most of your sample, if not all of it. Could be that the column's broken, or it's not installed correctly, and we've gone through column installation in the previous part of this presentation. May well be simply that the detector is not lit, and so make sure that the detector is lit in that scenario, so particularly with the flame ionization detector. It may also be that the column position is not correct, and that actually the column is positioned too high, and that actually we're injecting below the column in the vaporization chamber. Or it may be that actually there's no carrier gas. Next, we're going to have a look at some of the results issues that we can see. So if we're seeing low reproducibility of peak area, there are a variety of causes that could be generating this, from the concentration not being compatible with the dynamic range of the detector system. So if we're operating outside that range, that can cause issues. Might be that the column's not been installed, which is why we had a focus on column installation. Might be that the injection technique is not appropriate. Could be that there's a leaking syringe, or the septa is starting to wear, and therefore we need to look to replace the septa. Or it might be associated with the split flow ratio, and we need to have a look at that. In terms of the remedy, ensuring that we have the right sample concentration for the detection system is relatively simple. Look at using a different injection technique. Make sure that all of the consumable items are replaced on a regular basis. This includes syringe and septum. Monitor the flow and look to replace the inline filter if its lifetime is up. And then finally, if we feel that there is an issue with the column, look to reinstall the column. Poor sensitivity with increased retention time. The carrier gas flow rate may be too low. If the poor sensitivity is associated with normal retention time, then we could be looking at another or injector parameters are not optimized, so we're seeing some degree of variability. Could be a leak. Might be that the syringe is no longer gas tight, and therefore we're seeing some leakage on the syringe. It might be that the split injector temperature is too low, or failing that we are seeing some column issues, and that's resulting in a poor sensitive response from the detector. For retention time shifts, if retention time is seen to decrease, then the possible causes here are that the stationary phase has been deteriorated, either due to column bleeding or due to the presence of oxygen. Could be that we've got a leak, or that we've actually cut off so much of the column that we're starting to see the impact of cutting off those extra 10 centimeters having an impact in terms of the retention time. Hopefully that wouldn't be the case. In terms of the remedy, using a carrier gas free of oxygen and water will certainly help. Appropriate filters here would help massively. Look to reduce the column temperature to avoid that column bleeding. Potentially reinstall the column if we feel that it might be a leak. And then if the column length is causing a problem, then look to replace the column with a new column. If the retention time is increasing, then that could be a variety of issues, either something to do with the carrier gas or temperature issues. So in terms of the remedies, look to make sure that the septa and the column connections are all correct and well maintained. And then finally, if the pressure on the gas cylinder is low, look to replace the gas cylinder. We can now look at low reproducibility of retention time. A variety of different causes for this: poor injection technique, the sample size is too large, unstable column temperature, column might be in poor condition, the oven temperature program is too quick and therefore not reproducible. It might be that there's air leaking into the system at the injector or the carrier gas. In terms of solutions to remedy this, we could look at doing a better injection technique, look to reduce the amount that's injected, maintain and check the main oven door, make sure that the column oven temperature is being maintained adequately and the column door oven hasn't been left open. Look to reduce the column temperature ramp rate, particularly if you've been using fast GC. You may find the transition to standard GC a little bit traumatic in terms of that. And if it is a leak, then look to try and identify where that's coming from using an electronic leak detector and then repair. This list is by no means exhaustive. There are lots of other issues that I've not yet discussed, and to be honest, I could be here for many more hours going through all the possible items that could happen on a GC. There are other areas in particular I've not discussed but should be thought about very carefully when troubleshooting. So specifically looking at set to bleed, losing resolution, and also baseline oscillations, square wave peaks, and potential for contamination as well. And so that pretty much concludes the presentation. And hopefully what you've seen today is that we've got a really good understanding of the different components on a GC. And as well as that, we've then gone through how to install a column. And then the bulk of the presentation has been looking at a whole raft of different things that can go wrong on a GC, what to look for, and then more importantly, how to remedy them. And then finally, we wrapped up with these conclusions. I hope very much that you've enjoyed today's seminar, and very much looking forward to speaking to you again in the near future.